In November of 2025, a star wandered too close to something that, according to nearly everything astronomers thought they knew, shouldn't have been there at all. It was torn apart, instant by instant, its shredded remains spiraling into a glowing disk, bright enough to briefly outshine 10 billion suns, and the black hole responsible was sitting nearly 30,000 light-years away from where black holes like it are supposed to live. That single fact is what makes this discovery genuinely rare. Not just another star meeting a violent end. When a star strays too close to a massive black hole, the black hole's gravity pulls harder on the near side of the star than the far side, a mismatch strong enough to stretch the star apart. In a process astronomers call spaghettification, the shredded material spirals inward, heats up violently, and produces a brief, brilliant flare, an event called a tidal disruption event, or TDE for short. These flares are rare. On their own, a given galaxy only produces one, on average, roughly once every 100,000 years. Since the first ones were spotted using X-ray satellite data back in the 1990s, astronomers have confirmed only around 100 of them total. And here's the pattern that made this particular one so strange. Almost every tidal disruption event ever recorded has happened at the exact center of its host galaxy, precisely where astronomers expect the biggest black holes to be sitting. That's not a coincidence. Supermassive black holes and galactic centers are assumed to go together, for good physical reasons. So for decades, the standard strategy for finding a new tidal disruption event has simply been point your search at galactic centers, because that's where the black holes actually are. Astronomers already knew, in theory, that wandering black holes ought to exist somewhere in the universe, drifting through galaxies without ever settling back into a central position. But actually finding one was a different problem entirely. Outside of the rare moment they briefly disrupt a passing star, wandering black holes produce essentially no detectable light at all, making them close to invisible under any conventional search strategy built around scanning galactic centers. This one broke that pattern completely. The story starts with a research fellow named Robert Stein, who built an artificial intelligence system specifically designed to scan the entire sky for the telltale signature of a star being torn apart, rather than restricting the search to galactic centers the way earlier efforts had. The system began operating in August of 2025. Just 3 months later, it flagged an unusual flare, recorded by the Zwicky Transient Facility, a survey that photographs the entire northern sky every 2 nights using twin telescopes at Palomar Observatory in California. According to Stein, the discovery landed on a Saturday, and the team dropped everything, immediately triggering follow-up observations across multiple other instruments to confirm what they were actually looking at. Confirming it took real detective work. A doctoral student named Jonathan Carney at the University of North Carolina at Chapel Hill captured the spectra that helped nail down the interpretation, and NASA's Neil Gorell Swift Observatory delivered some of the most decisive evidence. Swift's ultraviolet and optical telescope measured the flare's temperature at roughly 30,000 degrees Celsius, squarely within the range expected for a stellar accretion disk forming around a disrupting black hole, and far hotter than most other astrophysical explanations could easily produce. Between the spectral data and the temperature measurement, the team was able to rule out other possible explanations and confidently identify the event as a genuine tidal disruption. The location is what made it historic. Catalogued as TDE 2025 ABCR, the flare occurred in a galaxy called WISE AJ0146.04-152214.7, roughly 750 million light-years away, in the constellation Cetus. Careful measurement placed the flare about 9.3 kiloparsecs, close to 30,000 light-years, from that galaxy's center. That's the largest offset ever recorded for a tidal disruption event found through visible light, easily surpassing the previous record holder. A similar event, found offset by only about 2,600 light-years back in 2024, itself already considered a genuinely unusual find at the time. The gap between that earlier record and this new one, roughly a factor of 10, gives a sense of just how far outside the normal expected range this particular black hole turned out to be sitting. The black hole responsible weighs in at roughly 1,000,000 times the mass of our Sun, and before this flare, it would have been completely undetectable, with no material actively falling into it. A quiet, wandering black hole like this one produces no light of any kind. The only reason anyone found it at all was the brief, violent moment it happened to catch and destroy a passing star. So how does a supermassive black hole end up drifting through the outskirts of a galaxy, instead of sitting at the center, where its enormous mass should have settled at long ago? The research team has proposed two competing explanations, and both trace back to the chaotic aftermath of galaxies colliding with each other. The first possibility is fairly direct. A larger galaxy could have absorbed a smaller companion galaxy, gradually stripping away nearly all of that smaller galaxy's stars over time, until nothing remained but its compact central core, and the black hole still sitting inside it. Essentially a ghost of an entire galaxy reduced to one drifting fragment. The second, more chaotic possibility involves three black holes instead of one. If a galaxy already had two supermassive black holes locked in a binary orbit around its center, a common outcome after an earlier galactic merger, and then a third black hole arrived from yet another collision, the resulting three-body gravitational interaction could have violently flung the smallest of the three black holes outward, ejecting it from the galactic center entirely. According to the team, continued observations of the debris left behind by this specific event may eventually help distinguish which of the two scenarios actually happened here. Either explanation points toward the same broader conclusion. Galactic mergers don't just combine stars and gas cleanly into one bigger galaxy. They can also fling entire black holes loose, sending million solar mass objects wandering through galactic outskirts, invisible and undetectable, for what could be billions of years, until the rare, random moment one of them happens to catch a passing star. According to Suvi Gazeri, a co-author on the study at the University of Maryland, the underlying assumption astronomers have operated on for decades is that supermassive black holes simply reside at the centers of massive galaxies. This discovery is direct evidence that assumption doesn't always hold, and more importantly, it demonstrates that wandering black holes, like this one, can actually be found systematically using ground-based visible light telescopes rather than requiring pure luck. That last part matters enormously for what comes next. Researchers expect the rate of tidal disruption event discoveries to jump dramatically in the coming years, from a few dozen found annually in the relatively nearby universe today to potentially hundreds or even thousands per year at much greater distances once next-generation survey telescopes come fully online, including the Vera C. Rubin Observatory and UNC Chapel Hill's own Argus Array. If wandering black holes like this one turn out to be common rather than exceptional, astronomers may be looking at an entirely new, previously invisible population of supermassive black holes scattered throughout galaxies everywhere, simply waiting for their next unlucky star, and until now completely absent from every catalog and every model built around the assumption that black holes stay where they're supposed to, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.